Okay, so that's about wave. A quick review. Can you read it out? What did I say wave is?
Wave is a disturbance travels through the medium when there is one and transfers energy from one point to another. That's from one point to another without causing any permanent displacement of particles.
So a wave is a disturbance that gets into a medium, and then as it gets into the medium, it will be transferring energy from one part of the medium to another. And the particles of the medium, if there's a medium, I will explain to you what I mean by if there's a medium. Like water, which is the medium through which a wave can pass through. The particles of the medium, like the particles of the water, will be displaced, jump up, jump down, or go up, go down, the particles. But after the wave has passed, the water particles will stabilize again and stay in their fixed position. Something like this. This is usually what we use to represent the wave. It goes this way, this way, this way. You see that? The water jumps up, goes down, goes up, goes down, goes up, goes down, goes up, goes down. Now, after the wave has passed, the water settles again and stays in its rest or undisturbed position. This is the rest or undisturbed position, isn't it? Okay. So now, when we are talking about wave, there are certain key words you need to take note of. First of all, it is a disturbance, and it passes through a medium, and it transfers energy through the medium. If there's any medium, and as it is transferring energy, because what happens will be spreading. As it is transferring energy, the particles of the medium will be displaced, but will not stay displaced permanently. So no permanent displacement of the particles of the medium. Right? Okay, now, types of waves. Types of waves. We can classify waves based on two criteria. The first one is whether it needs a medium or if it doesn't need a medium. So you said mechanical wave. Mechanical wave. What is a mechanical wave? If it does what? You need to be audible.
Based on what they taught you, say mechanical waves that require propagation of.
Okay, a mechanical wave needs a medium. Without a medium, it can't move, it can't travel, it can't propagate. For instance, sound. If there is no air, can sound travel in a vacuum? Like if we remove all the particles, matter in this entire space, and I'm making sound, can you hear me? You won't hear me if there's nothing, no air. Do you know that? That's why when people are in space where there's no matter, like no air between them, they can't hear each other. Like if you have two astronauts in space, they can't hear each other. They can't hear each other. They can't hear each other. You understand what I mean? Because sound requires a medium to travel. It has to be a matter. It could be air, it could be liquid, which of course is, for instance, water, or solid, maybe steel, what have you. Sound requires a medium. Without a medium, sound cannot travel. So sound is a mechanical wave. If it requires a medium, we call it a mechanical wave. A wave. These are waves that require a medium. Example, water waves, sound waves, earthquakes. Do you understand? Now, if it doesn't need a medium, it can travel without a medium. We call that what? Please, you need to be audible.
Electromagnetic.
We call it electromagnetic waves. Electromagnetic waves do not require a medium. They can travel through a vacuum. With or without a medium, they can move. Give me an example of an electromagnetic wave. And so on, radio waves, gamma rays. I just want us to look at the electromagnetic waves in its entirety. There are about 7 of them, depending on if you are separating radio waves from microwaves. Well, actually, the entire electromagnetic waves are radio waves, microwaves, infrared, which of course is heat, visible light, where you have red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, and gamma ray. These are the electromagnetic waves, right? In fact, I have listed them in the order of their increasing frequency. I will talk about frequency very soon.
That means gamma ray is the strongest.
Not necessarily strength, about strength. Gamma ray has the highest frequency. Frequency is actually the number of cycles it makes in 1 second. It's measured in hertz. We talk about that. So gamma ray has the highest frequency. Which one has the lowest frequency? Radio waves have the lowest frequency. Among the visible light, which one has the highest frequency? What are the visible light? You know Roy beef, red, orange, yellow, green, blue, indigo, violet, isn't it? So among the visible light, which one has the highest frequency? You can just tell me the letter. I'll tell you what the letter stands for. No, I told you when you are moving down like this, that is how the frequency is increasing.
Violet.
Violet has the highest frequency, okay? Which one has the lowest frequency among the visible light? Red. Right? So which among the visible light, which one has the highest wavelength?
Violet.
Check it. As you are going down, the wavelength decreases.
Red.
Red has the highest wavelength. Take note of all these. So we have started. This is the beauty of physics. You're enjoying it, isn't it? Interesting. So the visible light, the one with the highest wavelength is actually the longest wavelength. I mean wavelength, the visible light.
Red.
Red has the longest wavelength. Which one has the shortest wavelength? Visible light or?
Violet.
Violet has the shortest wavelength. Which one has the highest frequency?
Highest frequency is violet.
Violet, interesting. Which one has the longest wavelength of all the electromagnetic waves? Radio waves. In fact, radio waves have the longest frequency. Longest wavelength. Which one has the smallest frequency? Or the lowest frequency? Radio waves have the lowest frequency. The reason is, as you are moving down this line, the frequency increases, isn't it? But the wavelength decreases, isn't it? That means as the frequency increases, the wavelength actually decreases. So I was trying to tell you that if you name all of them like this, there will be 6 of them, 7 of them, 1, 2, 3, 4, 5, 6, 7. But sometimes radio waves and microwaves are mentioned together because radio waves and microwaves are actually the same thing. Microwaves are just radio waves of smaller wavelength or shorter wavelength. Is that not? Between radio wave and microwave, which one has a shorter wavelength? Microwaves. Good. Now, all of these are electromagnetic waves. They do not need a medium. Can gamma ray travel through a vacuum? Yes or no?
Yes.
Why yes?
Because it has the highest frequency.
It's not about frequency.
Because it has.
Look, this is the reason. Read this out.
Electromagnetic waves are waves that do not require a medium and so can travel through a vacuum.
Yes, electromagnetic waves are waves that do not require a medium and so can travel through a vacuum or space. All electromagnetic waves don't need any medium. They can just travel in space. That's why light can travel through space. Heat can travel through space because it doesn't need a medium. Gamma ray can travel through space. X-ray and whatever, microwaves, radio waves, they cannot travel through space. Thank God for that. Otherwise, we will not be able to see the light of the sun. Do you know why? Between the earth and the sun, you have space. Vacuum, isn't it? If light cannot travel through space, can you see the light of the sun? You won't be able to get to the earth, isn't it? If heat cannot travel through space, can we feel the heat of the sun? No. But if there's sound in space, like if there's a supernova, when you get to space physics, I will talk to you about supernova. If there's supernova in space, something that happens to stars, a loud sound in space, can you hear it on Earth? Why not? Tell me why you cannot hear it on Earth.
There's no space.
There's no matter, no medium for sound to travel. So, even two astronauts who are standing close to each other cannot hear themselves. Do you know? Actually, when they are in space, they communicate to each other with a phone. As I'm sitting close to you now, I'll be talking to you with a phone if we were in space. Because only radio waves and all other electromagnetic waves can travel through space. Sound cannot travel through space, so they can only hear themselves through phone calls, which of course uses radio waves. Do you understand? So you can classify waves based on whether it needs a medium to spread or propagate, or it doesn't need a medium. If it needs a medium, what do we call that? Example, we call that mechanical waves. Examples are water waves, sound waves, earth waves. If it doesn't need a medium, what do we call that? Examples are and so on. Interesting. Infrared, radio waves, and so on. Visible light. Okay, now all electromagnetic waves travel at the speed of 3.0 times 10 to the power 8 meters per second in space or in a vacuum. All of them, they travel at the same speed. What's the speed at which light travels in space?
3.0 times 10 to the power 8 meters per second.
Light travels at 3.0 times 10 to the power 8 meters per second because light is an electromagnetic wave. All of them travel at the same speed in space, right? Do you know the speed of sound?
Sound.
Yes, sound in air. It's even here. What's the speed of sound in air?
300 meters per second.
Sound travels at the speed of 300 meters per second in air. The light travels at this speed, 3.0 times 10 to the power 8 meters per second. Which one is bigger? The one per second. In fact, this is 300 million meters per second. This value, 3.0 times 10 to the power 8 meters per second, is actually 300 million meters per second. While the speed of, that's the speed of all electromagnetic waves in space, while the speed of sound in air is 300 meters per second. So, the speed of electromagnetic waves in space is about 1 million times faster than the speed of sound. Or 1 million times, or yes, faster than the speed of, as fast as the speed of sound. Did you get that? Light travels at a tremendous speed. In fact, there's nothing we know in nature that travels faster than light or electromagnetic waves. So their speed is the absolute speed. Is what?
Absolute.
That's the highest speed possible. That's the absolute speed, the highest speed possible. They may travel at different speeds in other mediums. So what I mean is, through solid, electromagnetic waves can travel at a different speed. Through water, they can travel at a different speed. Even through air, they can travel at a different speed. This speed is the speed they travel with in where? In a vacuum. Now, sound also travels at different speeds in different mediums. Let me zoom this in so that we can see it properly. See, the speed of sound in air, which of course is gas, is 300 meters per second. In water, which of course is liquid, is about 1,500 meters per second. This one is about 300, air is about 300 meters per second. Liquid or water, for instance, is about 1,500 meters per second. Solid, which is steel, is about 5,000 meters per second. So, which medium does sound travel fastest? That's in solid, right? Good. Sound travels faster. Sound travels faster in solid than in liquid, and faster in liquid than in gas. Do you know why it travels faster in solid than in liquid? Because the particles of solid are more closely packed together, so it's easier for the particles to transfer the vibration. You know, the way sound travels by transfer of vibration. One particle vibrates, transfers it to the next, to the next, to the next, to the next, and so on. So if the particles are closer to each other, the transfer will be faster, isn't it? Compared to the ones where the particles are farther away from each other. Which medium, which state of matter has its particles farthest away from each other? Which state of matter has particles with the highest distance from each other? Are you sure? Which state of matter has the particles with their distance farther? Gas, of course. Gas are far away from each other, the particles. That's why the speed of sound is slowest in what? In gas. Okay, remember we've talked about method of wave, classification of wave, based on whether it will need a medium or it will not need a medium. Let's go to another way of transferring it, of classifying it. I'm going to give you this note, right? So that we don't waste time. Classification based on how the wave moves compared to the direction of the vibration. That's another way you can classify it. Are you listening to me? Yes. Now, if the wave is moving in this particular direction, and the particles of the medium are also vibrating in this particular direction, in the same direction, parallel to each other, we call that longitudinal waves. For instance, if when I dropped the stone into the water, as the ripples were spreading sideways, the ripples were spreading what? You know, when you drop the stone in water, the ripples start spreading, and getting wider and wider. Assuming the water particles were also vibrating horizontally, same sideways, parallel, isn't it? We will call that what? But is that how the water particles vibrate? How do the water particles vibrate? Down, up, down. So is water wave a longitudinal wave? No, it is not a longitudinal wave, because as the wave is spreading in a particular direction, the water particles are not vibrating in the same direction, parallel, no. In fact, water wave is a transverse wave. For a transverse wave, as the wave is spreading in a particular direction, the particles of the medium will be vibrating at 90 degrees. At 90 degrees, perpendicular to it. An example is water wave, so that we can see all the examples. First of all, we can classify waves based on how the wave moves compared to the direction of the vibration of the particles of the medium. If the waves are spreading in one direction and the particles of the medium, like the water particles, are also vibrating in that same direction, parallel to each other, parallel to the direction of the vibration of the transfer of the wave, then we call that longitudinal waves. I want you to read this out. what I wrote in green, in red, and then in yellow. Let's start.
Direction or vibration of particles on medium is parallel to direction of movement of wave.
Good. The particles of the medium is vibrating sideways. The particles of the direction of movement of wave is also that same direction. And what's the name of that wave? Longitudinal wave. Examples are what? Sound wave and some earthquakes. There are some earthquakes that are longitudinal. Some are transverse. Now let's go to transverse wave. Read the explanation for transverse wave.
Transverse wave is direction of movement of wave is perpendicular to the direction of vibration of particles of medium. Example, water.
Water wave. So as the wave is spreading in this direction, the particles of the medium, like the water particles, will be vibrating perpendicular to it at 90 degrees to it, isn't it? An example is water waves. Now, all electromagnetic waves are also transverse waves. Did you hear that? So give me examples of transverse waves.
Infrared, gamma rays, X-rays.
Excellent. Water wave. Now, give me an example of a transverse wave that is also a mechanical wave. Excellent. And you deserve a knuckle. Interesting. That's cool. Water wave is transverse and it is also mechanical. Some types of earthquakes are also transverse waves and also mechanical. Right? Or the rest of this, electromagnetic waves, even though they are transverse, they are not mechanical. Why are electromagnetic waves not mechanical waves? Why are electromagnetic waves not classified as mechanical waves? Yes, no problem. The question is, why are electromagnetic waves not classified as mechanical waves?
Because they don't require medium.
Excellent. Electromagnetic waves do not require a medium. They can move through space. So the electromagnetic waves. But mechanical waves must need a medium, like matter, liquid, gas, solid, like sound, like some earthquake. All earthquakes are mechanical waves. Right? Interesting. I hope it's getting clearer. I like that. So let's move on. Why is sound a longitudinal wave? It's a question mark. Why is sound a longitudinal wave? Now this is how sound spreads. Look at these air particles when they are undisturbed. You know, all of them are equally spaced. The particles are equally spaced. Now, assuming someone starts speaking, the air particles, some part will be squashed, what we call compression. The part next to it will be stretched, what we call rarefaction. I represent compression with C, rarefaction with R. Then the next one, compressed, squashed. The other one, stretched, and so on. Okay, so you have compression, rarefaction, compression, rarefaction, compression, rarefaction, compression. In fact, see the way the sound wave was before it was disturbed. Right? Now, after it was disturbed, some parts squashed, compression, some stretched, squashed, stretched, squashed, stretched, squashed, stretched, until the sound moves from where it was produced to where it will be heard. Is that clear? Did you notice that as the sound wave is spreading sideways like this, the particles are also vibrating sideways? So what kind of wave do we call that? Longitudinal waves. So sound waves are longitudinal waves. Okay? Alright, so sound waves are longitudinal waves. The reason is, do you have a question? Oh, okay. Alright. By the way, I said the compressions are the squashes. Actually, the compressions are regions of high air pressure, where the pressure of the air is high, so the particles are squashed. The rarefactions are the stretches, where the air pressure is low. So rarefactions are regions of low air pressure. Spell rarefaction. Yes, correct. Rarefactio. Pronounce it. Rarefactions are what?
Or stretches are regions of low air pressure.
Good. While compressions are?
Regions of high air pressure.
Regions of high air pressure. And you see that as the air, as the wave is spreading in this direction, right? The particles of the medium, which of course in this case is air, will also be vibrating in this same direction, isn't it? That's why sound is what kind of wave? Longitudinal wave. What is a longitudinal wave? Be audible.
Is a wave that is parallel.
You have the idea. It's a wave in which the direction of spread of the wave is parallel to the direction of vibration of the particles of the medium. Interesting. Alright, now I need us to define some terms. Sometimes we need to represent waves with certain symbols. Are you ready for that? Okay, look at this. We start from, we use this sine curve to represent the wave. Like the peak or the peak are the crests or the compressions. The trough, represented with T, are the rarefactions. Are the what?
Rarefaction.
Okay, so it will climb, like when the water rises, falls, rises again, falls. As the wave is moving, the water particles can rise, fall, vibrating. And after the wave has passed, the water particles settles, or the water particles will settle again in their undisturbed position, isn't it? Okay, so the peaks are called the crests. Are called what? They can be represented by the compressions. The troughs are the rarefactions, okay? Or the region of low pressure. From one crest to the next, that's the adjacent crest, is called what? One wavelength. So a wavelength of a wave is the distance from one crest to the next crest, or the distance from one part of the wave to the adjacent corresponding path. This is what I mean. If I started from here, let me use a yellow line to show you. If I started from here, see, the particles are coming down here, is it not? First of all, they jumped up here, and they are coming down here, Where is the next place they are also coming down? Here they are jumping up. They are coming down here again. So if I move to this point, that's also a wavelength. So from here to here is a wavelength. Just like from crest to crest is a wavelength. From trough to trough is a wavelength. From sea to where is a wavelength. Okay, let me call it this D. From this D to where is a wavelength. Are you sure?
No. D to F.
D to F. Think of a wavelength as a complete circle. even though what we use is a cycle. So a wavelength is the distance traveled by the wave, horizontal distance traveled by the wave, when it completes one cycle. Think of it as a circle, because here it's half of a circle, like a semicircle. This is a complete circle. So A until it gets to C. So this distance A to C is a wavelength. If you start from C until it gets to E, this distance is a complete wavelength, isn't it? Because C to D is just half of a wavelength. Did you get that? So A to B is what? A to B is half of a wavelength. We use lambda, this letter, to represent the wavelength. Let me stretch it so that you see it better. You know that? Interesting. We get it. Wavelength. Velocity is frequency times wavelength. Let's move to that very quickly. So by the way, wavelength is the distance covered when the wave makes a complete cycle or oscillation. Now, amplitude, before we go to the other one, amplitude is what? You can think of amplitude as the height of the wave. But amplitude is actually the maximum displacement of the particles of the medium from its rest position. You know, this is its rest position. It is displaced from here to here. So the amplitude is this distance. So from a crest, the vertical distance between a crest and a trough is what? In terms of amplitude. The vertical distance between a crest and a trough in terms of amplitude is what? The vertical distance, this distance between a crest and a trough is what? How many is, in terms of amplitude, is what? Look at it. From here to here is one amplitude, is it not? Also from here to here is another one amplitude. So from crest to trough, I mean the vertical distance, is 2 amplitudes. Are you sure you got that? Yeah, let me explain that again. What do we call from here to here? Amplitude. So what will you also call from here to here? So from here to here will be how many? What now? 2 amplitudes. So 2A. Is that clear? Beautiful. Yeah, sharp. Alright. Amplitude is the maximum displacement of the particles of a medium from the rest or on the stop position. Yeah, of course, since it's about distance, the SI unit is meter. Also, wavelength, since it's about distance, the SI unit is meter. The SI unit, the symbol is lambda. The symbol for amplitude is, the symbol for wavelength is lambda. Symbol for amplitude is A. Now, frequency is the number of cycles made in 1 second. Like if the wave makes 50 cycles in 1 second, we say the frequency is 50 hertz. The SI unit is hertz. HC. So frequency is, read it out. The SI unit is what? Hertz, the number of cycles made in 1 second. But what's period? Cycle, the time is about time. So the unit will be what? Seconds. I hope you know the difference between frequency and period. Frequency is how many cycles it makes in 1 second. While period is the time it takes to make just 1 cycle. Anyway, there's a relationship between all of this. So let's go to that. We were talking about that. The formulas. Speed of a wave is frequency times wavelength, right? Yes. Period is 1 over frequency. You know that one? Or frequency is 1 over period. I hope you know it's getting clear right now. Interesting. Beautiful. So we will look at this quickly and then we move into something else. Watch this. Take a short break. This is what we call wave front. Take note of this. Wave front. What do I call that? The wave fronts are just lines we can use to represent certain part of the wave. Like if at a particular crest I draw a line, the next crest I also draw a line. The next crest I draw a line. All these lines are called wavefronts. Are called what? So the distance from one wavefront to another wavefront will give you what? Oh, good, one wavelength. Because from crest to crest is a wavelength. So one wavefront to another wavefront is a measure of a wavelength. So the distance between two adjacent wavefronts is one wavelength. So you can represent crest with a wavefront, another crest with a wavefront, or trough with a wavefront, another trough with a wavefront. Okay? Alright, let's look at this very quickly, and then that's an exercise. Let's go, read it out. Get ready. Here we go.
Each box represents one scene on both the horizontal and vertical axis and
1 second.
1 second on the horizontal axis.
Okay, it says each box represents 1 cm on both the horizontal and vertical axis, and 1 second on the horizontal axis. Okay? So, which sound wave is the loudest? By the way, the loudness of sound is affected by its amplitude. The bigger the amplitude, the louder the sound. Did you get that? The pitch of a sound is affected by its frequency. The higher the frequency, the higher the pitch. Do you even know what I mean by pitch? Notes, the note of the sound, like which one has a higher note? The first one. Okay, boys, usually have a deep voice, so low note or low frequency. Girls, high frequency. You get that? Like when you plug the thin cord, do you play any instrument? Like when you plug the thin cord of a guitar or a violin, that's high or low note? High, shrill. The thick one, low note because it's deeper. Okay, so you can think of the frequency as how many cycles, we already said this, how many cycles made in 1 second, isn't it? Without even wasting our time, let's look at these 3 waves, A, B, C. Which one has the highest frequency? Remember, frequency is the number of cycles made in 1 second. Just as you can think of how many cycles each of them made, because it's the same. Let's even see the first one. The first one has 1, 2, 3. Only 3 cycles. I hope you know from here to here is a complete cycle. Also from here to here is a complete cycle. Also a complete cycle. So this is 1, 2, 3 cycles. This one has 1, 2, 3, 4 cycles. This one has 1, 2, 3, 4, 5, 6 cycles. So which one has the highest frequency? C. So which one has the highest pitch?
C.
C. Interesting. You see how easy these things are? And they're cool. They're cool, I tell you. So which sound wave is the loudest? C. Looks like it's C. Because C has how many boxes? 1, 2, 3, 4 boxes. B has 1, 2, 3 boxes. A has 2 boxes. And we said each box represents 1 centimeter. So what's the amplitude of A? What's the amplitude? Are you sure? Amplitude of A. Amplitude is from here to here. 2 centimeters. 2 centimeters, you can change it to SI units. That will be what? Yes. SI unit is meters. So you said the amplitude of A is 2 centimeters. Change it to SI unit, which is in meters. What will it be? How do you change centimeter to meter? How do you do that? You divide by 100. So 2 centimeters divided by 100 will give you 0.02 meters. So the amplitude of A is actually 0.02 meters. The amplitude of B should be, from here to here is 2, 1, 2, 3. That's 0.03 centimeters, which is 0.03 meters, isn't it? So which sound is the quietest? A is the quietest, correct. Which sound wave has the lowest pitch? The lowest pitch is A because it makes the smallest number of cycles. Which sound wave has the highest pitch? C. Now calculate the amplitude of A, B, and C. We've done that already. Can you just give me the amplitude of C?
Amplitude of C is
Let me zoom it in so that you can see C better. So 1 box, 2 boxes, 3 boxes, 4 boxes. 1, 2, 3. 0.04 meters, which of course is 4 centimeters because each box represents a centimeter, isn't it? Alright. Alright, it says calculate the frequency and period of each wave. Calculate the amplitude of each wave, A, B, and C. We should be rounding off. How do you calculate the frequency? 1 over period? Yes, you can do that, but we don't know the period yet. You can even find the period, that's even good. Yes, we can do that. Let's find the period. But we can find a period. I'm happy that you said frequency is 1 over period. We can find a period. Remember, it says each box represents 1 centimeter on both the horizontal and vertical axis, and 1 second on the horizontal axis. That's what we call the time gain. 1 second per box. Each box is 1 second. Horizontally, time gain. Vertically, each box is also 1 centimeter. We call that Y gain. Y gain, you know. Alright. So if each box is 1 second, each box is what? 1 second, we say, right? Let me tell you. What? No. See, look at it now. On the horizontal axis. How many? Let me zoom it in so that you see. Starting from here to here is a wavelength now, is it not? How many boxes were covered from here to here?
How many boxes?
Yes.
2.
Are you sure? Box. This is a box, another box, another box, another box. So how many boxes? You're not seeing it clearly. It's not showing really. Oh, really? Come closer. Come closer. I need to see it. No wonder when I was talking about boxes, you were not really seeing it. Is it better here? Look, just look at it from here. Can we see the boxes? So how many boxes?
4.
1, 2, 3, 4 boxes. So each box is 1 second. So how many? What's the period?
4 seconds.
Excellent. You deserve a number. So that's 4 seconds. The period is 4 seconds. The period is 4 seconds. Because from here to here, where it covers 1 complete cycle, which is a wavelength, the time taken to complete 1 cycle is 4 seconds. The time taken to complete 1 cycle is what?
4 seconds.
What do we even call that?
Period.
So the period is 4 seconds. So how do you get the frequency now?
1 over 4.
Excellent. 1 over 4. That gives you the frequency. Did you see that? You see how easy these things are? Now, let's even use only that of C. It says calculate the wavelength of each wave. Let's calculate the wavelength of C only. Remember, the wavelength is the distance it covers when it makes 1 cycle, isn't it?
Yes.
So what's the wavelength? Can I remind you again the instruction? It says each box represent 1 centimeter on the horizontal. Look at it. Read it out. Each box represents
1 centimeter
on the horizontal and both on the horizontal and vertical axis. So each box represents 1 centimeter. Each box represents 1 centimeter horizontally. So from here to here, 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. So what's the wavelength?
Wavelength is 4 centimeters.
4 centimeters. You know you need to convert to SI unit, which is 0.04 meters. We know the wavelength, we know the frequency. Do you know we could have even calculated, okay, can we find the speed? That's the next thing now. What's the speed? What's the formula for the speed again?
Speed is equals to
Frequency times
wavelength.
wavelength. Since we found the wave frequency, I think we found the frequency to be 1/4. Right?
Yes.
So we do like do you have your calculator there? Let's even calculate the speed. Speed is V. Is frequency times wavelength. Frequency times wavelength. Frequency times wavelength. What did we get for the frequency you said?
1/4.
So that will be 1/4, which is 0. Okay, let me just write 1/4 times. What did we get for the wavelength?
Wavelength is 0.04 meters.
Interesting. We got it 4 centimeter, which is 0.04 meters year to year. 1 centimeter, 2, 3, 4 centimeter, which is 0.04 meters. So 0.04 meters. So the speed will be what?
0.01
Meter per second. Is it not?
Yes.
That will give us 0.01 meter per second. That's the speed. Is that clear?
Yes.
See how easy these things can be. Take note of all of these, okay?
Yes.
All right.